Hello everyone, we are here in a new video and continue with this series of videos of programming microcontrollers in assembly language. This time we have a very interesting topic actually. It will be digital outputs and delays. First of all, before starting, let me give you a brief introduction of why this is important to know. So, in embedded systems, creating precise time delays is a fundamental task. Delays are often required for tasks such as generating precise timing for peripherals, for example, for serial communication or for PWM signals. Actually, in PWM, the time is critical, okay? Then it is also widely used for introducing pauses between operations like debouncing buttons. If you still are not familiar with the debouncing term, basically it introduces a certain delay before actually triggering before triggering the action. Okay, so imagine for example that you press a button, and then that button won't immediately perform whatever it should perform, right? It will wait a certain amount of time and then it will trigger the action. So that is why knowing how to perform delays when creating a debouncing button is important. Also, it's widely used for synchronizing processes or waiting for hardware events. So, when working in assembly language, delays are created by executing a series of instructions that consume processor cycle. The duration of each delay is determined by the processor's clock speed and the number of instructions executed. This is the keyword, okay? Or the keywords processor's clock speed. This is very important to know, okay? And then I will show you later how you can realize about this value. But first of all, we have to know what is the architecture of the processor that we are using. You know, in the world of processors, there are two different types of architecture. On the left side, we have the hardware architecture, and then on the right side, we have von Neumann architecture. As far as I remember, and then as far as I know, hardware is newer than the von Neumann architecture, and actually most of the processors nowadays they use this hardware architecture. So the microcontroller that we are going to be using, it is the PIC16F887. It works with the hardware architecture. So now that we know that our microcontroller works with this specific architecture, we can go to determine the instruction cycle time, okay? And it is determined by the oscillator's frequency divided by 4 unless stated otherwise in the datasheet. This is because the instruction cycle generally consists of 4 clock cycles. That means that our microcontroller is going to perform 4 steps in order to complete one operation, okay? And these 4 steps are the following. The first one will be fetch, the second one will be to decode, then to execute, and finally to write back. So these 4 steps are mandatory performed to complete one operation. This is very important to remember, okay? If you are still not familiar with the frequency term, you should start to get familiar with, okay? And I will tell you why this is important. I have here a visual aid that will help me to explain this better. So if you take a look at this, it is stating that we have one cycle here, right? And then we have a wave or a signal that is being on a high value for certain amount of time and then on low value for another certain amount of time. If you realize, we are having here that the frequency of this signal is 1 hertz, okay? Or this is the same as 1 cycle per second. So the hertz unit, they state how many repetitions are happening in 1 second. So this is important. Imagine that I ask you to blink your eyes at 10 hertz. That means that you will be blinking your eyes 10 times in 1 second. That is very, very quick, actually. But how do we know what is the frequency of our microcontroller? Again, we are going to be working with this specific model of microcontroller, and then to know the exact frequency, we should look at the datasheet or this technical document provided by the manufacturer. In this case, Microchip is the company that builds this microcontroller. And then if we take a look at the documentation, we see here that the software selectable frequency range is from 8 megahertz to 31 kilohertz. Okay, this means that you can play around arbitrarily choosing which frequency you want your microcontroller to work with. In this case, you just have to remember that 31 kilohertz will be the minimum, and then 8 megahertz will be the maximum. Okay, this will be for the internal clock that the microcontroller has. You can attach external clocks, right? And then you can even increase this frequency to a higher value. But this time we are not going to use any external clock. We will work with the one that is built in the microcontroller. Okay, so for this example, we are going to choose the higher frequency, or the highest one. It will be 8 megahertz for the following example. Okay, now that we know which is the frequency that our microcontroller is going to use to work with, then we have to determine which is the real frequency. In this case, to get the real frequency, we are going to divide the 8 megahertz by 4, because of the 4 steps that the architecture of the microcontroller needs, right? Then this will be equal to 2 megahertz. Okay, this is the real frequency that we will have. Then, to get the cycle time, we need to divide 1 second by 2 million. Okay, this 2 million is basically it comes from this frequency, right? And then we get the result that each cycle time, it will last 0.5 microseconds, or this is equals, in engineering notation, 5e minus 7. Okay, or it will be equals to 0.000005 seconds. Okay, so now that we know the time that one cycle time will last, we have here a very simple example of 3 lines of code. Okay, we have the no operation, then we have decrement file and skip f0, and then we also have the go to operation. If we inspect each one, we have no operation. It will have a cost of 1 cycle. Then decrement file and skip f0, it will have the cost of 1 cycle again. But the go to operation, it will have a cost of 2 cycles. Just for these 3 lines of code, we have a total cost of 4 cycles, right? So the total time cost to execute these 3 lines of code, it will be 4 multiplied by 0.000005. Okay, and this will be equals to 0.00002 seconds. So these 3 lines of code will be executed in this amount of time. But you might be wondering, hey Alan, if I want to create 1 second delay, imagine how many operations I have to type or I have to write in order to perform 1 second delay, right? And then, yes, you're right, we will have to write millions of operations. But fortunately, we don't have to waste a lot of time typing one by one. And actually, I don't think that will be possible, because perhaps the memory of the microcontroller will run out, you know. So in order to mitigate all of this work that will involve to create 1 second delay, we can create nested loops, okay? And by using loops, we can multiply this 0.0002 seconds many times. So if I go here and then I start to using nested loops, we have here the 3 lines of code that we reviewed earlier, and then we have the total time cost. Okay, but what if we loop the previous code 200 times? Then we have to multiply this by 250 times, and our new total time cost will be equals to 0.0005 seconds. This is closer to the 1 second that we need, right? But we're still not there to 1 second. So if we loop again the previous code 100 times more, then we have a new total time cost, right? And it will be determined by multiplying 100 by 250 by 4 by the cycle time, and then we have 0.05 seconds. We are almost there to the 1 second that we need, but still we need to loop again the previous code 20 times more, okay? And then we have 20 multiplied by 100 multiplied by 250 multiplied by 4 multiplied by cycle time, and now we get the 1 second that we are looking for. Okay, so if you pay attention, then we will need to use 3 nested loops in order to create 1 second delay. Okay, now it's time to review what are we going to build. Okay, and then I have this very simple diagram, and basically what we are going to build is that we are going to attach an LED, okay, with its resistor, and then we are going to blink this LED 1 second, it will be turned on, and then another second it will be turned off, and we are going to loop that infinitely, right? So the LED will be blinking for 1 second. We have here the diagram with the power source, or the source power, sorry. In this case, it will be the pin for the microcontroller, okay? And then we have we have the direction of the current, we have the LED, and also we have the resistor, okay? But we need to determine which will be the value of the resistor, or which will be the resistance in this case, because according to the datasheet, the PIC16F887 microcontroller, it cannot supply more than 20 milliamperes. Okay, so this is important to know. That is the reason why we have to determine this resistor according to our needs. So in order to do that, we need to calculate this. Okay, according to the Kirchhoff laws, we have that the voltage is equals to, or the total voltage is equals to the sum of the voltage on each component. In this case, we only have 2 components, the voltage of the LED and then the voltage of the resistors. The sum of these 2 voltages, they will be equals to the total voltage supplied, in this case 5 volts. Okay, and then remembering the Ohm's law, the current it's equals to the voltage divided by the resistance. Then we can substitute the voltage of the resistor by the following expression, right? The total voltage will be equals to the voltage on the LED plus the current of the resistor multiplied by the resistance of the resistor. I know that this is redundant a little bit, right? But then, since we are looking for which will be the value of this resistance of the resistor, or resistor resistance, sorry, we have here the following expression. Solving by our resistor, we have the total voltage minus the voltage on the LED divided by the current of the resistor. Okay, and now we have this expression that will give us the value for the resistor. However, there are 2 incognitas that we do not know. Those are the voltage on the LED and also the current of the resistor. Okay, and now we have to remember, as part of the general culture for any electronic engineer, this is something that any engineer should know, right? There is a table that will give you the LED forward voltage according to the LED color, right? It's important to know that because according to the color that you will select, the forward voltage will be different. And of course, this value will change everything in the calculation, and then therefore the resistor value will be different. Okay. Um, Also, as part of general culture, right? The LEDs are designed to produce a set amount of light operating at a specific forward current, ranging from 10 to 20 milliamperes. Okay, so this means that any of these LEDs, they will work as long as we supply an amount of current in a range from 10 to 20 milliamperes. Okay, there are certain situations where power savings are important. Less current might be possible. Okay, we can supply less than 10 milliamperes. However, reducing the current to below, let's say, 5 milliamperes may dim its light output too much, or even turn the LED off completely. So this is something you have to keep in mind. So if you pay attention to this, that means that we can arbitrarily select how many resistance we want to supply to the resistor, and also we have to choose which LED color we are going to use to work with. So for this simple example, I'm going to work with the red LED, okay? And I want to supply the 10 milliamperes to my LED. So if I replace this value, okay, the voltage on the LED, in this case it will be 2.1, and then the current that I want to give to my LED will be 10 milliamperes. If I divide or if I perform the operation, I get a result of 290 ohms. Okay, this will be the value for the resistor that I'm going to that I'm going to use. Okay, however, the value that we got, or the theoretical value that we got, is 290. But if you go to a electronics store and then you ask for a resistor of 290 ohms, people, first of all, they will make fun of you, okay? And after that, they will tell you that that value does not exist because that is not a commercial value. So here on the left side, I have a table that will help us to select the resistor that has a commercial value. In this case, that value that is closest to 290 is this 300 ohms resistor. So that is the one that I will select. Okay. Then the last step here, or I put this visual aid. Basically, this is a high level flow diagram of what we're going to build. And then we have here step by step. First, we have to define the variables. Then we have to set up the port D pin 5 as output. Then we're going to turn on the LED. We will call the subroutine for 1 second delay. We are going to turn off the LED, and then we're going to call the subroutine for 1 second delay again. Okay, after this, it will be an infinite loop, and it will make our LED to be on and off for 1 second. If we take a look at the right side, we have the subroutine, and then we also have here the delay of 1 second with nested loops, applying this technique of multiplying 20 times by 100, and then by 250, by 4, and then by the cycle time. Remember that this cycle time depends on the microcontroller's clock frequency. Okay, so we have here already the flow diagram. Now it's time to go to code and implement this. Actually, I have already written this code here. Okay, and it is already here. It's quite simple. I have to define 3 counters because of the 3 nested loops, right? I change to the bank 1, the memory bank 1, in order to configure the 3D port pin 5 as an output, okay? Then I switch back to the memory bank 0, and then I set, or I turn on the LED with this instruction, right? I'm giving the output on the pin 5 for port D. Then I call the subroutine called time. Then I turn off the pin 5 of port D. I call again the subroutine, right? And then I go to the infinite loop tag in order to make this loop infinite, okay? And if we take a look at the time subroutine, we have here we have defined the constants. We have the 20, 100, 250, right? And basically here we are looping these 3 operations: the no operation, decrement file, and skip if 0, and last the go to operation, right? This is basically how it works. You can just freeze your screen at this point and then copy this code and use it on your application, or on the application that you need, and then you can arbitrarily play around with this value in order to either increment or decrement the number of seconds for this delay, okay? So this is how it works. I assume that you already know what each of these operations stands for or what they do, right? But it's time to build this. You see that it builds properly, and I do not have the material in order to build this physically, but we are going to use a simulator in order to demonstrate that this is working as expected. And there are multiple options for open source simulators. In this case, I'm gonna use Simul IDE. This is open source. I don't want you to download illegal software, please. And here, this is more than enough for the application that we are going to show this time. So if we scroll down here to the micro devices, here we have the PIC16F887 one that we are looking for, okay? Now, we also need a resistor. It is on the passive components. Here I have the resistor, right? I have the ground as well. And something interesting, I'm going to take the ammeter in order to visualize how many current our LED is having, okay? Of course, I also need the LED. Let me look for it. It is already here, okay? And I just need to plug everything. So remember, we're working with port D on the 5 pin, so I need to wire the D5 pin to my LED. Then I'm going to wire this to my ammeter, and finally I need to connect my resistor with the ground, okay? Before starting this simulation, I have to load the firmware to my microcontroller, right? So once that my code has been built, I need to take this direction where my project is located. I'm going to use my Files Explorer, or actually, you know what? I will load it directly. If I right click on the microcontroller and then click on Load Firmware, I can just paste this direction. Then if I go inside this default production, I have the hexadecimal file. This is the one that really matters, okay? And then I am going to load this file. You can see this message that the firmware was successfully loaded. And this time I'm going to use this 100 ohms. I'm going to change it later, sorry. And let me start this. You can see that this is starting, right? And you can see that the LED is blinking, okay? At this point, you can see that this is going even faster, I think, right? And that is because we have not configured the frequency of the microcontroller. You can see that this is at 20 megahertz, and it was blinking faster than in a period of 1 second, right? This is not what we were looking for. So we need to adjust the frequency to work with 8 megahertz because this is the one that we use for our calculation, right? So after I modified this and then I turn or I run the simulation, you can see that now the LED is on for 1 second and then off for 2 seconds. But still, the current that we are getting here is not the one that we calculated, right? And it is because we need to adjust the value for the resistor. If I adjust this to 290, that was the theoretical value that we obtained, we have a value close to 10 milliamperes, but again, we are not using the red LED. So let me change the color. We are working with the yellow one, but we need to work with the red in order to have the value closest to 10 milliamperes. So if I run and execute this again, we are getting the theoretical value that we obtained. There is a slightly difference, and that is because the impedance that is also playing in this circuit. Okay, but this is quite close to the 10 milliamperes that we calculated manually, right? But since 290 ohms is not a commercial value, I'm going to replace this again for 300 ohms, and this will be the final result, right? Still close to what we were or close to what we calculated, right? And just for fun, I want to show you what will happen if I give more than 20 milliamperes to my LDE. So let's say in this case I decrement the value for the resistor, let's say to 10 ohms. Okay, if I run this, you can see that my LED is getting 63 milliamperes, and actually you see that even the simulator is putting this with a red square, kind of telling you that this is dangerous, right? Not dangerous at all, but basically your LED will be burned out eventually while the time goes by, right? It will be burned out because of the high current that it is managing. So in order to keep this LED alive, right, it should work with a range from 10 to 20 milliamperes. So this is basically the practice for blinking an LED that we built, right? I hope you have enjoyed this video so far, and thanks for watching.